velocity profile, which is of course parabolic according to what was discussed in the elementary transport and what we discussed also briefly here. So for velocity. And this will be a steady state profile. So it means that it does not change anymore with increasing x, right? So what happens with temperature? We discussed previously when we just started discussing external flows that also for temperature we expect some boundary layer where temperature would change from the temperature close to the temperature at the surface Ts, right, to the temperature which is far away from the surface. And when we started discussing it, it was just flow over the surface, right? And this liquid extended to the infinite distance from the surface of this solid block, right? In this case, of course, we cannot assume that the distances are infinitely large because there is a finite diameter. So we can expect that there will be collapse of this temperature profile, and some profile will develop. So the question is whether this profile will change continuously with increasing x, or it will also come to some steady state like velocity does, and then it would not change anymore. And of course, this is the preferred situation. Then we can say, well, for this situation, we can actually solve the problem exactly because nothing is changing anymore, right, with x. This steady state, it means that with time, nothing changes. But it's questionable whether it changes or not with increasing x in terms of temperature distribution. So what experiments tell us is that neither T nor Tm, which is mean temperature over the cross-sectional surface area. Right, so it's mean temperature over cross-sectional surface area. So both of these properties remain to be functions of x. Right, so always.
What about velocity?
Velocity reaches steady state, it doesn't change anymore. After the distance, which we have denoted as xfd, right, so x fully developed, then it doesn't change anymore. But with temperature, it's different, okay? So what is interesting, though, is that another property which we can introduce, which is modified temperature, Ts minus T over Ts minus Tm, where Ts is temperature of the surface. So this property can actually reach a steady state value at some sufficiently large x, so that derivative of this modified temperature with respect to x is equal to 0. Right? It means that this property doesn't change anymore with increasing x. So this condition corresponds to thermally fully developed flow. So it means that this property, if it's written in the problem statement that it's thermally fully developed, it means that this property doesn't depend on x, which means that it's not a function of x anymore. So this can happen only if either qs double prime is constant or Ts is constant. So please note that cannot be and. Right? So it's either Qs double prime is constant or T is constant, right? It cannot be that both of these conditions are satisfied if we want to see that we have thermally fully developed flow. Also, what is written here is that this can happen only if, right? So if we see, for example, that Qs double prime is constant, it doesn't mean that we have thermally fully developed, right? Because that's not what it says. If we see that Ts is constant, it doesn't mean that we have thermally fully developed flow. Okay? So it doesn't work in the other direction. So for this, now I would like to derive some expressions or some preliminary expressions which would help us to solve the problem And solving problem, of course, will be finding distribution for Tm and for T. So you have a question at this point?
I answered it, man. Sorry.
Okay. So first thing I want to show is that if it's thermally fully developed, for thermally fully developed, H is constant. So convective heat transfer coefficient is constant. So I would like to show it. So what I want to do is just to take a partial derivative with respect to R now of this modified temperature Ts minus T over Ts minus Tm, so which is equal to minus derivative of T with respect to R over Ts minus Tm. I know that this is not a function of x, right? It's not a function of x because what's inside of the bracket is not a function of x, right? If we take derivative of what's inside of the bracket with respect to r, it's still not a function of x, right? So it is not a function of x. And if you look at this expression, it probably resembles you something, right? It resembles you what we got for h over k when we discussed external flow. So let me remind you this. We can write for any position in the surface that Ks double prime is equal to minus k liquid multiplied by derivative of temperature with respect to r at I equal to 0, which is surface. And at the same time, we can use Newton's law, which is h multiplied by Ts minus Tm for the same property.
What did the number sign mean?
What?
Not equal.
Sorry guys, just one
It's
thing.
just a not equal sign.
Not equal sign, yes. So this means it's not equal to, it's not number, sorry. It's not equal sign, yes.
So is that at r equals 0 or?
It is r equal to, right, so I equal to 0, should be I equal to 0, yeah, right. So here I'm not writing I equal to 0 because Ts is for I equal to 0, Tm is just the mean temperature, right? It's the same everywhere. You don't need to write that it's for I equal to 0, right? So now we can actually, from these two expressions, we can get h over k, which is, again, so minus dt over dr at I equal to 0. Divided by Ts minus Tm. So it's essentially the same expression as this one, except that here we require that it's for I equal to 0, but since it's not a function of x for any r, right, so because we don't specify r, then it should be also for I equal to 0, which belongs to the location of our liquid. So we can say that based on this, right, based on this, we can say that it is not a function of x, so not equal to, again. It's not a function of x, and k is not a function of x. So as a result, we can say that h is not a function of x. So in this case, we have shown in the most general form that for thermally fully developed flow, h is not a function of x, but only if we have thermally fully developed. Okay? So any questions at this point? Yes.
And the reason I was asking for the velocity is because in thermo we have like a problem that's like a pump here and a pump here, and they give you the m dot, what is that called? Mass flow rate, and it decreases between the 2 points. So,
Mass flow rate decreases?
Yeah, so I don't know if that's the
Yeah,
same
so
as.
it's not right. So mass flow rate decreases. It means that there is movement with acceleration, right? Unless you have changes in the diameter. In
No,
our case,
it's just a really long pipe.
no. I mean, look, it's either if mass flow rate decreases, right?
Yeah.
Flow rate, it's mass for the whole cross-sectional surface area per time, right?
Yeah.
If it decreases, then the and diameter is the same, right? Then there should be change in velocity or density of the fluid.
Yeah. Yeah, there is a change in density.
Okay, so density of the liquid is constant.
Okay,
right?
so
It's
that's
liquid.
why that's true.
Yeah.
Okay, got it.
It's liquid, yes. Right.
Got it.
It's
So earlier you said you were pointing at TM, and you said that TM is constant throughout the whole thing. What exactly is TM? Because I thought it was a function of x that was changing.
Yes, Tm in general should be a function of x. Remember, we discussed Tm just at the end of the class meeting last time. So we essentially defined it as the average temperature for any particular x. It's an average temperature over cross-sectional surface area, which we defined in such a way that the energy of the fluid per cross-sectional surface area is the same for real fluid, where we have distribution over T, right? T is a function of R. S the energy for the same fluid if we assume that all layers of fluid have the same temperature Tm. Right? So essentially, in a very simple way, we can say that Tm is an average over cross-sectional surface area. But it's not average over x. Okay? As a result, Tm can be a function of x. And it is. Just shown experimentally, right? So no other concerns at this point, right, guys? So okay, so now I would like to show some additional things
Teacher,
which will
do you have
prepare
your
you
book?
to solve the
Do you have
problems.
your book
I have a
with you?
question.
Yes.
How did you get the thermally fully developed equation, like Ts minus T?
Yes, so this is not something I got, right? It's just an observation from experiment, right? So essentially, all of this is based on experimental observations, right? So because we cannot really predict based on some fundamental laws, right? So it's the same for velocity. We just say, okay, so experimentally it's observed that this profile develops, right? And then it doesn't change anymore. This is the same as with temperature. We said that T and Tm are functions of x. They remain to be functions of x, just experimental observation, right? In general. Of course, there are some specific conditions when they might not be a function of x, right? But in general, we cannot say that at some point we wait long enough, right? So I mean, we consider x, which is sufficiently large, and then in all cases, they would become constants, you know, with respect to x. They will not, right? Although there are, of course, some special situations always when they might become constants, right? So it's experimental observation. But this property here, will become constant if we wait long enough. Okay, and this condition is called thermally fully developed. So based on experiment. So what I want to show next, so I can delete this, right? It's already started. So I want to show, so find relationship for thermally fully developed, so for thermally fully developed, find relationship between following derivatives. So I'm interested in dTs over, so dTs over x dt over x and also dTm over x. Right, so it's first derivative of Ts with respect to x, T with respect to x, and Tm with respect to x. Since we have two situations, so one of them is Qs constant. So let's first consider situation when Qs double prime is constant. Because we know that if it's thermally fully developed, then either Qs should be constant or Ts should be constant, right? So first let's consider Qs as constant. So my approach here would be to start by writing just QS in terms of TS and TM, which is writing essentially Newton's law. I can take derivative with respect to x of both parts of this equation. For the case of thermally fully developed, of course. If it's thermally fully developed, should I take derivative with respect to h? So of h as well with respect to x? No, right? Because it's constant. Then what remains are just derivatives of Ts and Tm with respect to x. But Qs is constant, it's not a function of x. So as a result, I can say that dTs over dx is the same as dTm over dx. Okay, so I got relationship between these two, the marginal derivatives. So now I need also to develop a corresponding relation for dt over dx, and for this I need to deal with this modified temperature. So Ts minus T over Ts minus Tm. So this time let me take the derivative with respect to x of this relation, because I'm interested in derivatives with respect to x. I know that the derivative of this property with respect to x is equal to 0. So let me just take derivative explicitly using chain rule. Right, so what should I do? I can essentially split it to two terms. And then use chain rule for both of these terms clearly. So I would like to continue on this side, so it can be deleted now, right? Yes. So let me start with the first term. I can write that it's dts over dx multiplied by 1 over ts minus tm. So a plus, but essentially I will get minus from the calculating of the derivative. So it is minus 1 over ts minus tm squared multiplied by ts. And here I have to write dts over dx minus dtm over dx. Right, so then we continue with the second term. So again, it is dt over dx. So some question? No, not yet. Okay. dt over dx multiplied by 1 over ts minus tm. So minus t over ts minus tm squared. And inside I have again so dts minus actually, right, so here I have minus overall, right? So I have to keep this minus. So I guess I can just write minus here, or it's better to just replace this plus with minus, not to confuse you. So minus here, and then plus here. So this minus here comes from this minus, right? And that's why I have plus here, because it's two minuses. So please check if you agree. It's just taking derivative using chain rule. So we know that it's equal to 0, and then we can rewrite it in terms of dt over dx, which we need to find. So we can write that dt over dx is equal to dts over dx minus ts minus t